You've been told Mars is inevitable, that it's not a question of if, but when. That rockets will keep getting bigger, engines more powerful, and one day you all watch humans walk across red dust as if it were the next logical step in evolution. It sounds unstoppable, it sounds heroic, it sounds like destiny, but destiny means nothing to physics. The universe does not care about ambition. It does not reward confidence. It does not bend for billionaires, engineers, or dreamers staring at the night sky. It operates on laws that are cold, precise, and completely indifferent to what you believe should be possible. And those laws don't clap for your progress. They test it. You imagine Mars as a distant goal waiting patiently for human footprints. Physics sees it differently. Physics sees mass, gravity, distance. Energy requirements so enormous they make everyday human effort look microscopic. The gap between Earth and Mars is not just millions of kilometers of empty space. It is a barrier defined by momentum, fuel ratios, radiation exposure, and survival limits. Every time you picture a rocket leaving Earth, you probably think of fire and smoke and countdowns. What you don't think about is the silent equation underneath it all. The one that determines how much fuel is required to lift fuel. The one that punishes every extra kilogram with exponential consequences. The one that quietly decides whether your dream is realistic or naive. Gravity alone is a ruthless gatekeeper. To leave Earth, you must reach escape velocity, a speed so high that falling back becomes impossible. That speed demands energy. And energy demands fuel. And fuel has mass. That mass increases the demand for more fuel. The cycle tightens like a fist. This is not pessimism. It is arithmetic. You live in a world where technology improves every year. Phones get faster. Cars get smarter. Machines shrink while power increases. It conditions you to believe progress is automatic and endless. But space travel does not scale like consumer electronics. It scales with physics. And physics is not impressed by trends. Reaching Mars is not about bravery. It is not about motivation. It is not even primarily about intelligence. It is about overcoming gravitational wells and carrying enough energy to cross an unforgiving vacuum without collapsing under your own mass. The hard truth is this: the universe sets the terms. You either meet them or you don't go. And those terms are far harsher than most people are willing to admit. You've been fed a story that feels smooth and unstoppable. Rockets launch. Reusable boosters land perfectly. Private companies compete. Headlines celebrate progress as if the path to Mars is simply a matter of persistence. Each success reinforces the narrative that humanity is on a straight line outward, that expansion into the solar system is the natural next chapter. It feels inevitable because progress on Earth has trained you to expect barriers to fall. But inevitability is an illusion created by momentum. Progress in one domain does not guarantee victory in another. Building faster computers or smarter software does not weaken gravity. Perfecting landing systems does not shrink interplanetary distance. The comfort of technological acceleration makes you assume that Mars is just a larger version of the same problem already solved. It isn't. It is a different category entirely. The universe does not reward trends. It enforces constraints. You can refine engineering. You can optimize materials. You can reduce costs. None of that changes the core demand. To leave Earth, an immense amount of energy must be generated in a short window of time to push mass upward against gravity. That mass includes the spacecraft, a crew, life support systems, shielding, supplies, return fuel, and the fuel required to lift all of it. The deeper you examine the stack, the heavier it becomes. This is where the story begins to crack. Every kilogram added for safety increases fuel requirements. More fuel increases total mass. Increased mass demands even more fuel. The loop does not scale linearly. It escalates. The dream of redundancy, comfort, and long-term survival directly collides with the ruthless math of propulsion. You've been encouraged to think bigger rockets solve the issue. But bigger rockets are not magic. They obey the same equations. Doubling size does not double capability in a simple way. It compounds structural demands, fuel ratios, and energy limits. The laws remain unchanged no matter how impressive the launch looks from the ground. There is also the quiet assumption that time alone will solve it. That waiting a decade or two guarantees breakthroughs. But physics does not age. The same equations that governed rockets 60 years ago still govern them now. Efficiency can improve. Materials can lighten. Yet the core relationship between mass, thrust, and fuel remains stubbornly intact. The story you've been told is emotionally powerful because it aligns with human optimism. It tells you that determination inevitably conquers obstacles. But space does not respond to determination. It responds to thrust-to-weight ratios and energy density. It answers only to numbers. And when you strip away the excitement and look directly at those numbers, the path to Mars stops looking like destiny and starts looking like a negotiation with laws that cannot be persuaded, pressured, or inspired. At the center of this entire challenge sits a single, unforgiving relationship: the rocket equation. It does not care about ambition. It does not soften for innovation. It simply defines how much velocity a spacecraft can gain based on how much propellant it carries and how efficiently the propellant is expelled. And hidden inside that relationship is a brutal reality: the growth is exponential. Velocity does not increase in a clean, proportional way when more fuel is added. To gain a little more speed, a disproportionate amount of propellant is required. To gain enough speed to escape Earth and then travel toward Mars, the required propellant fraction becomes overwhelming. The spacecraft quickly turns into a flying fuel tank, where most of what is launched exists only to push the rest forward. This is not a design flaw. It is mathematics. The equation reveals that the final velocity depends on the exhaust velocity of the propellant and the ratio between the rocket's initial mass and its final mass after fuel is burned. That ratio is where the trap lies. If higher velocity is required, the initial mass must grow dramatically compared to the final mass. The more ambitious the mission, the more distorted that ratio becomes. Consider what that means in practical terms. A mission to Mars demands not only escape from Earth's gravity, but also precise trajectory adjustments, deceleration upon arrival, and possibly ascent from the Martian surface for return. Each phase requires additional velocity changes. Each change compounds the mass ratio problem. The fuel needed for the later stages must be carried during the earlier stages. That extra mass increases the fuel required at liftoff. The chain reaction begins long before the rocket leaves the ground. Adding safety systems, radiation shielding, food supplies, spare parts, and life support redundancy makes sense for survival. But every addition pushes the mass upward. The equation responds without sympathy. More mass demands more propellant. More propellant demands a larger structure. A larger structure demands more propellant still. The growth accelerates faster than intuition expects. Chemical propulsion, which relies on the energy stored in molecular bonds, has inherent limits to exhaust velocity. That limit caps how efficiently momentum can be transferred. No matter how refined the engineering becomes, chemical reactions release only a finite amount of energy per unit mass. The equation reflects that ceiling. This is why rockets are staged, shedding mass along the way to partially escape the exponential burden. Even so, the majority of what launches from Earth is propellant. The payload, the part that actually matters, is a small fraction of the total. For deep space missions with human crews, the margin becomes thinner and more unforgiving. The rocket equation is not an obstacle to be debated. It is a boundary condition. It defines the cost of velocity in mass and energy. And when applied to the scale required for sustained human missions to Mars, it exposes just how narrow the path truly is. To even begin a journey to Mars, the energy requirements are staggering. Every launch demands overcoming Earth's gravity, a force that grips with relentless intensity. The planet's pull is not a suggestion. It is a strict rule that cannot be negotiated or circumvented. To escape it, a spacecraft must reach escape velocity, a speed of nearly 11 kilometers per second. Achieving this requires energy on a scale that dwarfs almost every terrestrial experience. Every maneuver, every kilogram, every second in flight multiplies the total demand. Chemical rockets, the technology that has carried humans into space so far, are extraordinarily powerful. They burn fuel with violence, converting stored chemical energy into kinetic energy to push mass upward. Yet even at maximum efficiency, chemical energy has severe limits. The energy density of the propellants imposes a ceiling on the speed and mass a rocket can carry. You can refine engines, make materials lighter, or optimize the structure, but the ceiling remains. The universe does not reward cleverness over chemistry. The distance to Mars introduces an additional, unyielding barrier. At its closest approach, Mars is still tens of millions of kilometers away. Crossing that void is not a simple matter of maintaining thrust. Spacecraft must follow precise trajectories dictated by orbital mechanics. Each trajectory requires careful calculation of velocity changes. Accelerating, decelerating, and correcting paths across vast, empty distances. Small errors compound over millions of kilometers. The farther the journey, the smaller the margin for mistakes. Precision becomes survival. Carrying humans multiplies the challenge further. Crewed missions demand life support systems, shielding from cosmic radiation, enough food and water for the journey, and redundancy in every critical system. Each of these necessities adds mass, and each extra kilogram requires more propellant, more energy, and more structural support. The relationship is not linear, it is exponential. The more you try to protect and sustain life, the harder the energy problem becomes. Every improvement in safety or comfort amplifies the demand for power, creating a spiral that chemical rockets struggle to escape. The vacuum of space offers no assistance. There is no friction to slow momentum, but there is also no medium to absorb energy or stabilize travel. Once launched, the spacecraft carries all its energy within it. Unlike machines on Earth, which can draw power from grids, fuel tanks, or continuous supply, a Mars-bound vehicle is entirely self-contained. Every joule, every gram of fuel must be calculated and carried from the beginning. Even before considering landing, returning, or surviving on Mars, the initial energy investment is monumental. The spacecraft must not only reach the planet, but must do so on a path that allows deceleration and controlled descent. Every stage requires careful distribution of energy and mass. The margin for error is almost non-existent. This is why energy, not technology, is the true barrier to Mars. Innovations can reduce inefficiencies, improve safety, and refine propulsion. They cannot break the physical ceiling imposed by fuel energy density and the enormous distance between planets. The universe demands energy, and it demands it in amounts that push human engineering to its very limits. The scale of the problem is not an abstract obstacle, it is a concrete, unforgiving boundary that governs every attempt to reach the red planet. Here, as the first harsh realization, reaching Mars is not primarily a technology problem. It is an energy problem. Most people imagine that the challenge is in building better rockets, smarter guidance systems, or more efficient engines. They assume that human ingenuity alone will carry us across tens of millions of kilometers. That assumption is comforting, but it is dangerously misleading. The true obstacle is the physics of energy itself. Every kilogram sent into space must be accelerated to enormous speeds. Every piece of equipment, every gram of food, every drop of water adds mass. That mass requires fuel, which adds more mass, which in turn requires even more fuel. The exponential relationship between mass and propulsion is not something clever engineering can bypass. It is written into the laws of physics. You can optimize, refine, and iterate endlessly, but the ceiling remains. Chemical rockets, which are the foundation of all current spaceflight, are bound by the energy stored in chemical bonds. These fuels release a finite amount of energy per unit mass. You cannot magically make them more powerful without changing the chemistry itself. No matter how lightweight the structure or how precise the navigation, the total energy required to transport humans safely to Mars and back is constrained by the limits of these fuels. Even the most advanced rockets of today are only barely capable of leaving Earth, and the majority of their mass is devoted entirely to propellant. The scale of energy required for Mars is not incremental. It is massive. Tens of millions of kilograms must be accelerated to escape velocity. Trajectories must be carefully calculated to intercept Mars at exactly the right moment in its orbit. Deceleration is just as critical as acceleration, and each adjustment consumes more energy. Every addition to the payload multiplies these demands, creating a scenario where small improvements in comfort or safety can require disproportionate increases in fuel. Even beyond propulsion, energy governs life support. Humans need air, water, food, and protection from radiation. Every system designed to sustain life adds mass. Every extra kilogram adds energy demands to overcome gravity and reach orbit. The spiral of energy consumption grows faster than intuition allows, trapping ambitious plans in an invisible web of mathematics. The harsh truth is that human will alone does not overcome these limits. Motivation does not cancel mass. Ambition does not create extra energy. Progress in materials or design can only chip away at inefficiencies. It cannot change the fundamental ceiling imposed by physics. To truly make Mars reachable, humanity would need a breakthrough in propulsion, something that dramatically increases energy density, reduces mass constraints, or both. Without such a leap, attempts to colonize Mars remain trapped in a scale problem that current technology cannot escape. This realization forces a mindset shift. Stop thinking of Mars as a destination that is inevitable, because humans are clever. Start seeing it as a physics problem that demands respect for energy limits, mass ratios, and propulsion ceilings. Understanding this truth is not pessimism, it is clarity. It forces planning, innovation, and strategy to align with reality. And once that clarity is accepted, only then can solutions begin to take shape in a universe that will not bend for hope alone. Now comes the second uncomfortable truth. Even if the energy problem could be solved, the human body itself becomes the weak link in any journey to Mars. Every human system evolved under the protective conditions of Earth, gravity, atmospheric pressure, magnetic shielding, and a delicate balance of temperature and radiation. Remove those protections, and vulnerabilities explode. The body is fragile. The laws of physics do not soften for biology. Microgravity begins to destroy the body from the first moment it takes effect. Bones lose density. Muscles weaken. The heart struggles to maintain blood flow. The longer the exposure, the more pronounced the deterioration. Months spent in zero gravity are not a gentle inconvenience, they are a systemic assault. Even when astronauts return from low Earth orbit, rehabilitation is long, painful, and never fully restorative. Now imagine extending that time frame to the 6 to 9 months required for a one-way trip to Mars. What seems manageable in theory becomes a profound physiological crisis. Radiation adds in another layer of brutal reality. Earth, as magnetic field, and atmosphere act as a shield against cosmic rays and solar particles. Mars, and the space between, offer almost no protection. The energy levels of these particles are high enough to penetrate spacecraft and human tissue, damaging DNA, increasing cancer risk, and threatening cognitive function. Every hour in transit compounds the risk. The more shielding added, the more mass the rocket must carry, and the more fuel is required to overcome gravity. Once again, the laws of physics create an inescapable trade-off between survival and feasibility. Isolation and confinement intensify the challenge. The human mind is not designed for months of silence, monotony, and the psychological pressure of being millions of kilometers from Earth. Mental resilience is tested continuously, and even small cognitive impairments can have catastrophic consequences when one mistake can be fatal. Social dynamics, monotony, and lack of external stimuli are all amplified in the vacuum of space, yet these factors cannot be mitigated without increasing mass and energy demands. Every protective measure, every system designed to maintain life, feeds back into the original energy problem. Radiation shields, thicker hulls, food storage, water recycling systems all add kilograms. Those kilograms increase fuel requirements, which increases structural mass, which again requires more fuel. The cycle compounds. The human body, designed for the comfort and safety of a planetary surface, becomes a liability in the vacuum of space. Survival is not a certainty, it is a battle against physics itself. Understanding this forces a cold reckoning. Mars is not simply distant, it is hostile to biology by design. No amount of ambition or willpower reduces this hostility. Every trip is a negotiation with the universe, where every added system for survival carries an energy cost that pushes the mission closer to the edge of feasibility. The dream of colonizing Mars is not merely a challenge of engineering, it is a direct confrontation with the fragility of the human form. To face this truth requires abandoning comforting illusions. It requires acknowledging that every extra kilogram for safety, every protective system, every second of extended travel magnifies the energy barrier. Human fragility and physics are intertwined, and until both are addressed in unison through revolutionary propulsion, radical life support innovation, or genetic and biomedical breakthroughs, the path to Mars remains a gauntlet with no margin for error. Survival is not optional. Physics ensures it is always the first and hardest challenge. Here is the third harsh reality. The cost of a Mars mission is not just measured in money or technology, it's measured in risk, and risk concentration in space is absolute. On Earth, failures are inconvenient, costly, sometimes tragic, but rarely final. Systems fail, accidents happen, and people adapt. In deep space, every failure carries consequences that are immediate, inescapable, and often irreversible. The environment outside Earth does not forgive mistakes, and the margin for error shrinks with every kilometer. A damaged heat shield on re-entry could mean instant destruction. A malfunctioning life support system could slowly suffocate a crew. Navigation errors or miscalculations in trajectory could leave humans stranded in the void, with no possibility of rescue. Every single system must operate perfectly because there is no backup planet, no emergency crew to parachute in, no hospital within reach. The risk is concentrated, magnified, and relentless. Space is indifferent to human ambition, and physics guarantees that every misstep carries maximum consequences. The pressure of absolute dependence on flawless operation influences every decision, from mission design to daily tasks. Redundancy becomes a necessity, not an option. Every life support system must have backups. Every critical system must be doubled or tripled. Every component must endure stresses far beyond what would be considered reasonable on Earth. But redundancy comes at a cost. Each additional system adds mass, which adds fuel, which adds structural complexity, which demands even more fuel. Risk and energy are linked, forming a feedback loop that is impossible to ignore. This concentration of risk exposes the limits of human ingenuity. Humans are capable of remarkable problem-solving, but ingenuity alone cannot override the laws of physics or the exponential relationship between mass, fuel, and distance. The more complex the mission, the greater the probability that a single failure could escalate into catastrophe. Even the smallest oversight or miscalculation can multiply across systems, leaving no room for recovery. Every innovation, every attempt to improve safety amplifies the energy requirements. Radiation shielding, life support redundancy, emergency supplies, and structural reinforcements all increase mass, which in turn increases fuel requirements, which in turn increases structural demands. The rocket equation does not bend for caution, optimism, or ambition. The universe does not reward careful planning with leniency. It rewards solutions that obey fundamental limits. This is why Mars is more than a destination, it is a gauntlet. Every stage of travel, from launch to transit, from landing to surface operations, from return to Earth, concentrates risk in a way that is rarely appreciated. The farther from Earth, the fewer options exist for mitigation. On Mars, a simple malfunction is not inconvenient. It is life-threatening. The universe does not negotiate, and physics ensures that risk grows with ambition. Understanding this reality forces a perspective shift. Mars is not simply a technological challenge. It is a test of human resilience under conditions where failure is final and survival is precarious. Every decision about mass, fuel, and redundancy must account for absolute consequences. Cost is no longer abstract or financial, it is a measure of survival. Ambition without respect for these concentrated risks is not bravery, it is recklessness. The lesson is brutal but clear. The universe rewards preparation that aligns with physics, not optimism. To survive Mars, every kilogram, every joule of energy, every system must be accounted for. Risk is the true currency of deep space, and no mission can succeed without paying it in full. Survival is not optional. It is dictated by the unyielding laws of the cosmos. It is time to confront a brutal perspective. Human will alone does not overcome the laws of physics. You have grown up believing that determination can move mountains, that perseverance conquers impossibility. That mindset works on Earth, in classrooms, businesses, or sports arenas. But space does not care about motivation, courage, or moral resolve. It operates on immutable principles: mass, energy, momentum, and radiation that do not yield to ambition. Every desire to reach Mars collides with these boundaries. Willpower cannot cancel the exponential demands of the rocket equation. Motivation cannot reduce the kilograms of fuel required to accelerate mass to escape velocity. Ambition cannot rewrite the physics of life support or radiation shielding. Every personal effort, every innovative idea, must exist within the rigid frame of natural law. Ignoring that frame is not bravery, it is delusion. The universe does not negotiate. It does not offer shortcuts or favors. Every calculation, every adjustment, every improvement in engineering still bows to fundamental limits. Every additional kilogram, every extra system, every enhancement in comfort or safety compounds the energy problem, tightens the constraints, and increases the challenge. The laws of physics are not adversaries that can be persuaded, they are boundaries that must be respected. Humanity has achieved incredible feats, but the journey to Mars exposes the gap between ambition and reality. Propulsion, life support, energy requirements, and survival are all interconnected. Solve one without addressing the others, and the mission fails. The fragile human body, the limits of chemical fuel, the immense distances, and the concentrated risks of deep space are all part of a system that does not bend for optimism. Success requires understanding and obeying the system, not wishing it away. This is the shift in thinking that must occur. Stop romanticizing human conquest of space. Stop imagining that courage alone can overcome physical law. Stop believing that sheer will is enough to bend reality to your desires. Ambition must be grounded in knowledge, strategy, and respect for limits. The path to Mars is not an exercise in inspiration, it is a challenge in physics. Every decision, every calculation, every design choice must honor the rules imposed by energy, mass, and environment. The boundaries are not optional, they are absolute. Crossing them requires innovation, yes, but innovation within the framework of reality. Breakthroughs in propulsion, energy storage, or radiation shielding might make Mars feasible. Incremental improvements and motivational speeches will not. To confront this reality is to strip away illusions and embrace clarity. It is to see Mars not as a destination promised by optimism, but as a problem defined by physics. Understanding this is uncomfortable because it challenges everything society teaches about perseverance, success, and dreaming big. Most people are not willing to internalize that the universe is indifferent. They cling to hope, to inspiration, to stories of heroes defying odds. But hope does not generate thrust. Inspiration does not create energy. Bravery does not override orbital mechanics. Respect for limits is the only way forward. The hard truth is simple. Mars sits at the edge of what chemistry, mass, and biology can tolerate. Your ambition will not move it closer. Your will not alter its laws. The universe will not reward dreaming over calculation. Success is reserved for those who understand the boundaries, respect them, and act within them. Anything else is fantasy. The real lesson of all these brutal truths is that reaching Mars is not about courage, motivation, or even incremental technological progress. It is about understanding the fundamental physics that govern every step of the journey and adjusting thinking to match reality. Mars is not a goal humanity deserves because of ambition or ingenuity. It is a problem that demands a solution on an entirely different level. Ignoring that fact is a recipe for failure. Stop thinking of rockets, fuel, and spacecraft as mere tools. They are not enough. The challenge begins with energy. Every kilogram of payload, every drop of water, every shielding plate, every ounce of food, and every crew member multiplies the total energy required to leave Earth, travel millions of kilometers, survive in transit, and land safely. The energy required is not a number that can be stretched by determination or motivation. It is a ceiling set by chemistry and physics. Until that ceiling is dramatically raised, Mars is unreachable for humans on a large scale. The human body is another limit that cannot be wished away. Bones weaken, muscles atrophy. The immune system falters and radiation damages DNA over prolonged exposure. Each solution to protect life, radiation shielding, improved life support systems, or redundancies adds mass. Each additional kilogram increases fuel requirements, which compounds structural and energy demands. Biology and physics are intertwined, and one cannot be solved without accounting for the other. Optimism does not protect against these realities. Risk concentration is the third unavoidable factor. Every failure in deep space is final. On Earth, mistakes are often recoverable. In transit to Mars, a single malfunction can mean death. Life support systems, navigation, propulsion, shielding all must operate flawlessly, because failure is not just a setback, it is absolute. This reality forces choices and compromises. Every safety system added creates more mass, which increases energy demands, which in turn heightens the risk of failure during launch or transit. It is a paradox of survival. Protecting life adds risk elsewhere, and physics ensures the trade-offs are brutal. The mindset shift is unavoidable. Mars is not a destination for optimism alone. Incremental progress, clever engineering, or improved management cannot bypass the physical limits. Humanity must either revolutionize propulsion, discover radically denser energy sources, or redesign life support and radiation protection in ways that dramatically reduce mass. Without such breakthroughs, the mission remains a fantasy dressed up in ambition. This understanding changes perspective. It forces focus on what is physically possible rather than emotionally desirable. It emphasizes preparation over hope, calculation over inspiration, and realism over myth. The dream of Mars cannot survive naive enthusiasm. It requires alignment with the laws of physics. Only when energy, mass, biology, and risk are considered as interconnected, non-negotiable constraints does a path toward Mars begin to appear viable. Ultimately, the lesson is stark. dreams interplanetary colonization must bow to reality. Motivation alone cannot solve exponential fuel requirements, cannot protect fragile human bodies from radiation and microgravity, and cannot mitigate the concentrated risks of deep space. The universe does not reward hope, it rewards understanding, planning, and innovation that respects the laws governing energy, mass, and life. Anything less is wishful thinking, no matter how heroic it feels. Now comes the moment of truth. The journey to Mars is not a story of heroism or ambition. It is a confrontation with reality, with laws that do not bend for hope, courage, or desire. If humanity truly wants to reach the red planet, it must face the universe honestly, without illusions, without comfort, and without excuses. Dreams alone will not launch rockets, protect life, or overcome exponential energy demands. Only clear understanding and deliberate action can make the impossible possible. Stop romanticizing space travel as if it is an inevitable march forward. Stop assuming that technological progress automatically grants access to distant planets. Stop believing that willpower, optimism, or sheer determination can overcome mass, momentum, radiation, and biology. The universe does not negotiate. Physics does not compromise. Every kilogram, every joule of energy, every protective system is a debt that must be paid in full. Failure to account for these realities is not a lesson learned. It is a catastrophe waiting to happen. The challenge is simple to define but brutally hard to overcome. Energy must be generated at levels far beyond what current chemical propulsion allows. Mass must be reduced or offset in ways that do not compromise survival. Life support must protect fragile humans against radiation, microgravity, and isolation. Risk must be minimized in an environment where failure is absolute. Every solution must exist within the constraints imposed by physics, not just within the limits of imagination or budget. This is not a call to despair, it is a call to action. Respecting reality is not giving up, it is preparing to succeed. The universe does not reward hope, it rewards precision, understanding, and innovation that aligns with the rules that govern matter and energy. If humans are to set foot on Mars, it will not be because of courage alone. It will be because breakthroughs in propulsion, energy storage, radiation protection, and human sustainability finally meet the scale required by physics. Until then, every mission is a lesson in humility, a reminder that ambition without comprehension is vanity. Now is the moment to stop fantasizing about planting flags and building colonies. Now is the moment to confront the cold, indifferent truth. The universe sets the terms, and humans must meet them or fail. Every plan, every calculation, every prototype must acknowledge the brutal arithmetic of mass, fuel, energy, and biology. There is no shortcut, no magic solution, no substitute for preparation that respects these limits. The final reality is clear. If you want humanity on Mars, start by facing the wall honestly. Study the physics, question assumptions, innovate where energy, mass, and life intersect. Understand that the dream is fragile because reality is hard. Anything less than alignment with the laws of the universe is fantasy dressed in ambition. The margin for error is non-existent, the cost of ignorance is absolute, and the universe waits for no one. The challenge is stark. Humanity, as future beyond Earth, is not guaranteed. Survival on Mars is not a right. It is a problem to be solved with ruthless respect for physics, relentless focus on energy and mass, and uncompromising commitment to human life. If ambition alone drives action, the journey will end before it begins. If understanding guides every choice, then Mars, distant and harsh as it is, may finally become attainable. The universe will not forgive mistakes, but it will reward those who prepare with precision, clarity, and unflinching honesty. The path is narrow, the stakes are absolute, and the opportunity belongs only to those willing to confront reality without flinching.